Bismillahirrahmanirrahim. Welcome to the lecture. My name is Abdur Rahman and my roll number is 16TE22. In today's lecture, we will discuss about the introduction of digital filter, that what are digital filter and in what purposes do we use them. So let's start. First of all, there are two major properties or in which we can use our digital filter. The first one is signal separation and the second is signal restoration. So, and what is meant by and we have noise added in them. So in order to separate both noise and signal from it, the process used, the filter use is no filter is used, and we use signal separation for in it. And the second type, that is signal restoration, is done by filters. So in that case we have a distorted signal that is attenuated and its power is lost, and the shape of signal is deformed or distorted, so we use the filters to restore our original signal. So moving on, there are two main categories in which the filters are divided. The first one is analog filter and the second is digital filter. So what are the properties of analog filter? Analog filter is cheap and it is fast in its action, and it has a large range in time domain as well as in frequency domain. On the other hand, our digital filter is more जो है, has a high level of performance that we can use. We can obtain better results using a digital filter. So moving on, we have responses, three type of response of a filter. Number one is impulse response, secondly step response, and thirdly the frequency response of a filter. So how do we implement our filters? So to implement our filter, we convolve the original signal, that is x of n, with the response of filter, that is in most cases is represented by h of n, so known as filter, and this process is also known as filter kernel. So in another property, that is when we integrate our impulse response, we get our step response. Similarly, the impulse response, when the FFT, fast Fourier transform of an impulse response, is taken, we obtain the frequency response of our filter. So the values that are represented in frequency response are in dB. So what is dB? dB is the way of expressing ratios between two signal. For example, if we have two powers, power 1 and power 2 of a signal, and we want to represent it in the form of dB, so we take the log of p2 over p1 and multiply by 10. So this is called the dB, also known as decibel unit. So how can we represent our signal in time domain and frequency domain? So in time domain, we represent our signal in the form of amplitude versus time plot, and in the frequency domain we represent our signal in the form of amplitude versus the frequency curve or frequency plot. So a step response shows the information in time is modified by the system. Step response is also, we can say that the step response shows that how the information in the time domain is modified by using the filter, and similarly the frequency response shows that how the frequency is changed with the help of using a different filter, that when we use a filter, so what change does it make on the frequency of the system, that is known as frequency response, that is shown in frequency response of a filter. Another concept is that if we have a good performance in time domain of a filter, then the results are in bad performance in frequency domain. That are they both of these are inversely proportional. That if we have bad performance in time domain, so we get a good performance in frequency domain in filters. So in time domain we have three basic parameters in which in order to see that our filter is better or not, three responses are seen, or three parameters are seen. The first one is step response, and the secondly is overshoot, and third is phase of the filter. So step response should be good. That means that if in these examples given below we have two step responses. In the first image, the step response is too much, and time taken to reach the maximum value is greater, so it has poor step response. On the other hand, we have a good step response, that is the transient region in which the filter move from lower values to higher value, that is very less, and transient time is very less, so it has a good step response. Then our next is the overshoot of a filter. So in order to have a good filter, we should not have a overshoot. In the first image we have overshoot, that is the value is not settling quickly, as it is oscillating on when it reaches the final value. And similarly, next is the no overshoot, which is desired one, and as the signal approaches the desired value, it doesn't oscillate there, it moves on and stays constant. And the third parameter, that is known as phase. Though, so we should have a linear phase, that is whenever the phase changes, our output should phase and input phase should be in linear with each other. So moving on to the frequency domain parameters, then that what parameters should be seen in the frequency domain. So first one is the roll off. That means that whenever we should have a fast roll off in order to have a good filter in frequency domain, as slow roll off means the transient time is taken is greater, and in fast roll off the transient time or transient response is very less. So we have a good fast roll off. And in order to have the next parameter is ripples, we should not have any ripples in our frequency domain plot. That means if we have ripples, we should there should be attenuation, and different properties of the filter will be changed. So in order to get a good response, we should have no ripples in our response. And the third and last one is the stop band attenuation. That means that when the filter approaches the minimum value or zero values, the attenuation should be less, and good attenuation should be formed, so that whenever it reaches zeros, it moves towards constant. Not like in the time domain, we had an overshoot, and the oscillation were there. So similarly, in the case of stop band attenuation, no oscillation should be found in the response in order to have a good filter. Moving on towards the types of filter, that how many types of filters are there and how can we create them. So basically there are four types. The first one is low pass, high pass, second thirdly band pass, and the fourth one is band stop or band reject filter. So first of all, low pass. What is low pass filter? Low pass filter means that only low frequencies are allowed in to pass in that filter. Similarly, its opposite is high pass. That means the low frequencies are blocked and high frequencies are only allowed to pass through it. And similarly, by the combination of these two, we can make band stop and band pass filter. Band stop means that only a certain frequencies are blocked, all other frequencies are uh, or are permitted, and we can say that only a certain region or a certain band is stopped. And in this case, we have two pass bands and one stop band. And similarly, in the case of band pass filter, only a certain band is allowed, all other band frequencies are stopped. So moving on, how can we create a high pass filter? There are two methods. The first one is spectral inversion, and the second one is spectral reversal. So spectral inversion, what does it mean? It means that we change the spectrum of the we take an input signal x of n and multiply it with a response of this filter and with the impulse response, and when we subtract them, so we obtain the high pass filter. That is in this form, that is we low frequencies are blocked and only high frequencies are allowed. And the second one is spectral reversal, which means we take a low pass filter and we reverse its values. That is, where the values were high, we block that value, low frequencies were blocked, and the high frequencies that were stopped are allowed. So we get a high pass filter. In order to get a band pass filter, we convolve our low pass and high pass filter. So in that case, we get our band pass filter. So only certain band is passed and all the other frequencies are stopped. In another form, in order to get a band pass is by using a band stop filter and all void Gaussian noise filter. So we can get a band pass using that, which will be studied in this next. That means if we want to get a band stop, we add the low pass filter, that is only that allows only low frequencies, and the high pass filter, we add both of these filters in order to get a band stop. So in order to get a band pass from the band stop, we only do that. For example, we have this band stop filter and we subtract it from a constant filter, or we can say that, or we have a constant value of all over the frequencies. So we subtract that each other and we get a band band pass filter, that only a certain band is allowed. So that's all for today. Thank you. Keep watching my videos. Assalamu alaikum.